SwayamPrabha. Digital India. Educated India.
Next one is machining. Machining is a process wherein which the material is removed from the workpiece in the form of chip to produce the shape whatever we want. So, here this is a turning process we do. So, you can do by turning, drilling, milling. There are so many processes: turning, drilling, milling, okay, grinding. These are some of the processes I am just listing it down. So, all these processes what we do is we try to use a tool which is harder than the workpiece, harder, and which is in contact with the workpiece, and then it tries to remove material in the form of chip. So, when this is getting done, as I told you, during the process there is a temperature rise. A typical example is this, because here when it is in contact there is going to be friction. So, tool, workpiece, you will have a friction. So, this friction increases the temperature and you try to produce a chip. So, the temperature tries to dictate the material, and the temperature has to negotiate. If the temperature is very high and if the material deforms, then the geometry whatever we try to retain will not be accurate. So, here are some of the processes which I have told, I have just put in front of you. So, and then I have also said what are all the different materials can be done, what are the different applications, these are just a glimpse. Then what is the material removal rate. So, you can see here I have put it 21. Why is material removal rate important? Because it will try to dictate the time required for producing. And the next is tolerances, and the last one is roughness. As I told you earlier, roughness is very important when you are in contacting surfaces, and tolerances because you have to mate, and then so these are the tolerances we can do. So, turning and facing I have taken little bit. Turning is a material removal process wherein which we use a single point cutting tool. So, it moves whose major motion is parallel to the axis of rotation of the workpiece, and facing. So, if I wanted to reduce a diameter, so reduce a diameter. So, here this is along the is parallel to the axis, the tool moves parallel to the axis. So, this is called turning. If I move perpendicular to the axis, then it is called as facing. So, this is turning and this is facing. Okay. The dimensional accuracy depending upon the machine, you have precision lathes, you have precision machines. So, you can try to go to very small dimensions possible. For example, you can even go today with 0.01 millimeter, it is possible today. So, because there are precision lathes which are come. So, the dimensions and accuracies I have already talked, so I have just given in detail. Next, when I talked about milling, so milling I said drilling is the 2-point cutting or multi-point, two cutting edges you will have. In milling what you will have is you will have multiple cutting edges. So, you will have multiple cutting edges. This multiple cutting edges when it is rotated, it tries to remove material as chips. You can see here how the chips flies and falls. Milling is a cutting operation in which the material is removed by rotating a multiple tool cutter. So, again here depending upon the axis, it can be vertical axis, it can be on horizontal axis. Right. Vertical axis you try to cut a profile or you try to cut pockets. So, profiles and pockets can be cut, profile and pockets can be cut, or any other shape, right. So, it can be 3-dimensional. Horizontal is predominantly used to make slots, grooves and etc. Okay. So, I have given it, and here we talk about cycle time. Cycle time is important because cycle time in turn is related to the material removal rate. Next is grinding. Grinding falls under the category of secondary process. So, grinding falls under the domain of finishing. That means to say, here the material removal rate will be very less and the finish will be very high. In these two, material removal rate will be very high and RA will be very low. So, here we are not bothered about material removal rate to a large extent, we are more worried about surface finish. So, here we talk how accurate it can produce. So, you see there is a paradigm shift. Here time was talked about, here finish is talked about, here appearance is talked about, or functional requirements are talked about. So, here we do not focus on material removal rate. Okay. So, grinding is a process. The only difference between milling, turning and grinding is, here what happens is the tool is nothing but abrasive. So, they are random in nature. Several of these abrasives are put together, they are stuck to each other by a bond. Okay. There are several bonds, vitrified bonds, shellac bonds and other things. So, they are stuck to each other and then you try to give a shape to the abrasive bonded. So, and that bonds, and it is called as a abrasive wheel. So, this wheel rotates at very high RPM and then it tries to grind the surface. Okay. So, here the grinding is a process that removes material from the workpiece using a tool made out of abrasive particles of irregular geometry that can be embedded on the surface of a rotating wheel. So, the wheel speeds generally today we talk about 1 lakh RPM easily, but in general what we talk about in lab scales, academic scales and all, or in machines whatever you get today is 1000 RPM to 5000 RPM you can get. Like handheld, you can get up to 5000 RPM. See, 1 lakh RPM, it has to have a stable structure, rigid structure. And generally, when you talk from the designer's perspective, we have hand hold grinders which rotate speeds between 1000 RPM to 5000 RPM. It's pretty high. So, that is why what we do is when we try to grind, we try to hold it by 2 hands and then start doing it. The cycle time is relatively low. As I said, the material removal rate is less and the finishing is high. So, the cycle time is pretty low. The dimensions whatever you can get is pretty high. So, if you are looking for very tight tolerances, then after the machining operation, we always try to do a grinding operation to get the required tolerance. Now, I will I have put a glimpse of the non-conventional where the tool is not in. So, in subtractive process, as I said, the one is conventional and the other one is non-conventional. Okay. Conventional means the tool is in contact, So, when the tool is in contact, the material removal rate is high, the surface finish what you get is good. So, when you talk about non-contact, the tool is not in contact. So, what are all the possible tools? We use electron as a tool, we use photon as a tool, we use electron, photon, we use plasma as a tool, we use chemical etching as a tool. So, electrons, what happens is it can it can lead to a spark or it can do an electron machining directly. So, here we use photon which is nothing but laser. So, then we use here plasma which is the fourth state of material and chemical etching. Okay. The next one, last one is going to be the jet. So, jet can be in water. So, all these things are subtractive process. Since the material is not in contact, the tool is not in contact with the material, naturally the material removal rate is going to be extremely low and the power consumption is going to be high. You can never compare a non-conventional process with a conventional process. Okay. And all these majority of the non-conventional process are energy intensive. The photon laser which is used today, the efficiency of a laser while machining is around about 15%. So, electron can be done in two ways. So, what we do is we have electrodes, this is negative and this is positive, in between we have a dielectric. So, we bring this to as close as possible and then we apply a potential. So, when it is brought very close to each other and when you apply a potential, there is going to be an ionization going to happen between these two guys, and once the ionization is matured, there is going to be a spark. The spark means it is a sudden surge of electrons and it is going to move from one side to the other. The number of electrons are pretty large, the bunch of electrons are pretty large. When they try to hit at the surface, it is going to create a spark. The ionization is matured, spark is created. When it tries to hit at the workpiece, so this is your workpiece, this is your tool. So, now what happens? There is going to be a melt vaporization phenomena and material is going to be removed. So, wherever you have a harder workpiece where the tool cannot be used for machining, then we go for electron as a tool and then we do machining. And if you do not want this this system, so what we do is we try to have an electron, okay, we try to have a tool, we try to have a workpiece, okay, and then I put it inside a vacuum and then I start the electrons to hit at the workpiece. So, here it is also again melt vaporization, but it is happening inside a chamber. So, this process is called as electron beam machining and here it is called as electric discharge machining. So, the discharge happens, so melting happens and the material is removed. So, here the tool whatever I said can be in terms of a solid tool or the tool can also get into a wire form. So, with whatever is the basic principle I use here and then I start machining. Wherever you have a very hard material to machine, we generally go for this process. So, that is called as electro machining or electro discharge machining. Okay. So, here wire is used, I have explained all these things. So, cavity cut or it is otherwise called as die sinking and people start machining it. When you move towards plastic, the most commonly used process is injection molding process. Here it is a secondary process. So, what happens is you have a heated plastic which is extruded into extruded process. You remember extrusion we saw, extruded, and there we saw about metal, here it is polymer, extruded into a hollow tube. This is a tube and then the mold is closed, hollow tube, it is extruded, right, and then this portion is closed, okay, and then once it is closed, what we do is through this tube bottom side we try to push air, or you can even try to crimp it here and push air from the top. Both sides are possible. So, here in this example we have used pushing air from the top. So, once the air is pushed from the top, this is a viscoelastic material polymer. So, it tries to expand and the air is given enough or the volume of air is at is made sure such that the volume of this container or slightly higher is there. So, then what happens, all the viscoelastic material gets expanded and touches the die surface. So, whatever is the die surface and impressions on the die surface is getting transferred to the exterior of the polymer, and after this what we do is we hold it for some time such that the curing of the polymer happens and then we open the die and then what you get is the product out. So, this is a process which is blow molding process. Since you see lot of pearl pet bottles around or lot of mineral water bottles around, I thought I should explain this process. The entire process takes hardly 5 seconds or 10 seconds depending upon it, and you can have multiple dies at the same time. So, one shot you might get 3 or 4. So, this is a secondary process I have just put because polymers are also growing in a big way to make products today. When we talk about sheet metal process, here is a process which is frequently people try to get confused. One is called as punching and the other one is called as blanking. When you talk about metal forming, there are two categories. One is called as bulk forming and the other one is called as sheet forming. Wherever you have a larger surface area, it is sheet forming. Where where the volumes surface area is not very large, then we call it as bulk forming. In bulk forming, we apply lot of force to deform the material. Here comparatively it is slightly less. Okay. So, in sheet metal forming, the most common thing which people always get confused is punching and blanking. When I try to take a sheet, I try to create a impression, or I use a punch, I create an impression and pierce a material out. Whatever gets out of this ring, if I make it as a useful part, then that useful part is produced by a process called blanking. Whatever part I produce which gets out, and if it is a scrap, then that is called punching. Work, scrap, right. So, here punching is whatever comes out of it is not used. So, then it is called as punching. So, you can have progressive punching. So, you can also have washers. So, first outside is punched and then next internal is punched, possible. So, you get a donut structure like this on a sheet metal. Okay. So, punching is a shearing process in which the scrap slug is separated from the workpiece when the punch enters into the die. Blanking is a process in which the piece of the sheet metal that is separated from the punch action is required finished product, and it is leftover sheet metal is the scrap, then it is called as blanking. Okay. So, the coins whatever we use, the currency coins, all of them are done by blanking, and then it is done by stamping. You try to get the impressions like one embossment, whatever they do it on the coin. Next one is forging. As I told you, if you have a bulk, if you have a surface area not so large, so then it is called as volume, surface to volume ratio if you do, and if the surface area is very less, then the process whatever we use is called as forging. So, forging, what we do is we try to take a material, and here you should understand, you try to take a material, you try to heat the material. So, the load whatever you apply for deformation is less. If you do not heat the material, the load is very high. So, that is what I said, if you go back to the manufacturing process, pressure, temperature, time, all are linked. So, in a process you can have temperature and pressure. So, this is an example for it. So, depending upon the temperature, the force applied is less or more. Okay. So, you can do it at hot state, you can do it at warm state, you can do it at room temperature state. So, when you talk about a very large surface, the entire surface, and it is a prismatic surface, if it has to be machined, prismatic surface has to be machined, we call a process called as planing. So, planing is a process wherein which we use a single point cutting tool to produce a flat surface on a prismatic very large area. We are not talking about the bed size will be very large. For example, the lathe complete bed will be planed. Okay, the saddle, complete 1 meter long saddle will be planed. So, those very large where the bed size is what. So, the process what we use is called as planing. When the process area, when the workpiece size is small, then we call it as shaping. So, the only difference is here the bed moves. The tool is a single point cutting tool which is almost a constant. Here the tool moves and the bed is constant, that is the difference. And here you can make flat surfaces, you can make V surfaces. So, all are possible by this process. The next interesting one is called as broaching, which very rarely we use. Broaching, what happens is, here we use multi-point cutting tool and it is a finishing process. Okay. So, here the tool is like your corn. So, corn, so it is something like this, right. So, you try to pull the tool through your workpiece. So, initially it is of a smaller diameter, and then as and when it keeps moving, it tries to expand the diameter and then finish. So, here the difference in diameter will be maximum of few millimeters, or it will be less than a millimeter. The last operation is heat treatment. So, heat treatment is, you have made a shape, you have made a size, but you wanted to play with the mechanical property alone. So, what we do is we try to heat the workpiece, and then after heating the workpiece, we try to leave it in the atmosphere, furnace atmosphere, or we try to bring it out and then we try to quench it. So, here what happens, the shape is fixed by the machining process, size is fixed by the machining process, only the mechanical properties keeps changing. Heat treatment is a process wherein which it is heating and cooling of metal to change its physical and mechanical property. The shape does not change, the size does not change. So, what is the advantage? It refines the existing non-uniform structure. So, that means to say a structure means inside a microstructure, the grains will be large, the grains will be small because of the machining operation. So, there will be not non-uniform distribution of stresses, mechanical or compressive stresses on top of the surface. So, if you want to refine them, so that is possible by heat treatment. Internal stresses can be relieved, the grain size can be refined, and the improvement of toughness can happen. Toughness is in turn required because you want to enhance the fatigue behavior. Fatigue behavior you want to enhance. So, that is what we do. So, if you make a grain size smaller, then it is the workpiece is going to demonstrate a hardness is going to be high. So, if it is the grains are large, then it is going to be toughness going to be large. Okay. So, this affects the mechanical property and the physical property of the material. So, the hardening, which involves heating of steel and keeping it at an appropriate temperature until all the pearlite is transformed into austenite, and then quench it rapidly in water or oil, you can do it. So, basically here what are we trying to demonstrate is, we are trying to demonstrate heat treatment wherein which temperature, time and ambience are important. So, if you see that temperature, time, cycle is there. So, something like this, you have cycles, and when we try to do it, the ambience, it can be quenched, oil quenched, you get a different profile. When you try to put it in the furnace, you get a different profile. When you put it in an ambience where it is full of nitrogen, you get a different response. So, that is what we are trying to say. So, the temperature at which the austenite rapidly takes place depends upon the carbon content in the steel. So, the next one is tempering. Tempering is nothing but I try to heat the steel and then quench it and harden to an adequate period of time, so that the metal can be equilibrated. So, you see there tempering color of steel. So, if you try to play with the heat treatment, now you can try to play with the color. So, today what people are trying to talk about is, I will make a shape, then I will do heat treatment. When I do heat treatment, it tries to introduce a color which tries to remove the painting operation. Okay. So, today just by playing, see, you see the normalized plate, quenched plate at 350 degrees, then you do 400 degrees tempering, and then at 540 you see a different color is coming, 590 you see a bluish color coming. So, just by playing with the temperature, we are able to change the color. So, this is a good information which people have started working from the designer's perspective. You get the shape, put it inside, and then you try to play with the heat treatment, you get a color which is getting impregnated without any operations. Okay. The heat treatment, the higher temperature can result in higher ductility, but lower strength, a compromise. A lower tempering temperature will produce lower ductility, but a higher strength and hardness. In practice, appropriate tempering temperatures are selected, which will produce a desired level of hardness and strength. So, the other process is annealing. So, in annealing, it is the heat treatment. In this heat treatment, material are heated up to a desired temperature, which is held for a specific period of time before the material is slowly or rapidly cooled down, depending on the type of material. The process refines the grain size. So, if you look at it, initially a cold state, that means to say you have done a metal forming, and then you heat it, what happens, the high stress areas are dissipated, then a recrystallization happens, then a recrystallization leads to grain growth happens. So, you see here the grain size are changed from one to the other, such that you try to get a different mechanical property. So, here what did you do? You did not change the size, you just changed with the grain structure. And if you have carbon which is internal, by just playing with the heat treatment, we can move the carbon all get around to the grain boundary and it gets precipitated along the grain boundary. Normalizing involves a heating steel. Here I have taken only an example of steel. You can also try to do with copper, aluminum, anything. Okay, for everything there is a heat treatment cycle, you have to watch out for it and then start doing it. I am walking through only steel because steel is predominantly used material for primary structure, load bearing area. So, and then keep it at a temperature for a period of time and then cool it in air. So, these are discs which are cut and they are undergoing normalizing structure. The resulting microstructure is a mixture of ferrite and cementite which has a higher strength and hardness but low ductility. So, now what you do is, after doing this, you try to take it once again to heat treatment and then you try to change the grain structure and start converting these billets into flat rolls, coils possible. So, just play with the heat treatment. So, some of the design guidelines. So, for casting, the shrinkage can cause induced stresses and distortion in casting components. So, the section thickness. So, here if you have an abrupt change, it will always try to introduce, you will not have uniform cooling. So, there will be a possibility a defect might be caused. So, and there can be a lot of internal stresses. In order to avoid it, whenever you try to do casting, you try to give a radius and avoid the sharp edges, so that you can try to get a better performance, and shrinkage is also not there. When you try to forge, the parting line, what is a parting line? Parting line is when you have two surfaces, when you have a product, the parting line surface, this is a parting line because you generally make with two dies. If you look at the bottle example, we have demonstrated. So, here if you see here, the parting line can be here or it can be on the other side, 90 degrees rotated can be a parting line. This parting line is important because this parting line is decided based upon the strength which gets or the load which gets applied onto the on the product. So, if you do a wrong choice of your parting line, the strength of the product falls down drastically. And second thing, parting line is always decided because the die has to be separated. You can't make through a single die. So, you always make it through a split die. So, how should be the geometry on both the dies, that will be decided by the parting line, or moment I know the parting line, I can take that decision. So, parting line decision as far as plastic parts are concerned is a big challenge. This is okay. Suppose you are trying to make a pencil box. So, the symmetry on the pencil box is very difficult. So, now making a parting line is also deciding a parting line such that it can withstand loads is a challenge. If you have bottle cylindrical part, it is a easy job. But if you have something like a skewed geometry, then it is very difficult. So, here that is what I was trying to talk about. The parting line should be in the plane perpendicular. So, in the bottle, so this is the bottle, perpendicular means 90 degrees to the axis of the die motion. So, no portion of the parting line should be inclined more than 75 degrees from the principal parting plane, and much shallower angles are desirable. So, this is what. So, here we have, this is very important, let it be a metal part, let it be a polymer part. When you try to use die, so parting line is very important. So, here I have given the radius, depth of the rib to boss. So, rib is nothing but this is a rib, okay. So, or a boss. So, the corner radius, and I have given the fillets. So, if you want to produce a part like this and then you want to do a sheet metal, just as an example, in the computer, desktop computer, you have the server. So, there you have a sheet metal part. So, you see various geometries like this are pierced because the heat has to be extracted. So, here if you, instead of making this, it is always easy to make this. So, here what we do is we just expanded the width and then we made this thin, so that we try to get the required output. So, this is not recommended, this is recommended. Thin walls are recommended, thick walls are not recommended, because these thick walls can try to distort over a period of time. So, in extrusion, what we studied about the pipe or the rod which is getting extruded in metal. In polymer also extrusion is possible. So, avoid sharp edges, that means to say you always try to take cylindrical, never try to take a square extruded part. Then be generous in giving the internal and the external geometry. Here are some materials which we have given, and look at the corner radius. For aluminium and all it is 0.75, fillet radius is 0.75. For ferrous it is 1.5 and 3. So, depending upon the material, the fillet radius is also done. So, all these informations are available in books, in standard books. For example, you can look at data books, wherein which different process these guidelines are given. So, you have to go through that while deciding the geometry for the die. So, this is called as an unbalanced die. So, this is called as a balanced die. This is desirable, this is not desirable. Sharp edges are never desirable in punching operation. It is always good to have a filleted radius, because sharp, when it is piercing, making a die is also a challenge, because if it has to be punched, so you have to have a punch which is square. Making a square geometry is little difficult. So, if you can make a filleted one, so the sharp edges can be avoided. So, these are some more for stamping. So, ensure the maximum stock is utilized. For example, I do not know how many of you have seen, when you walk out, you will also see rubber pad, wherein which different footwears are cut at varying angles. So, what they have done is they have maximized the utilization in producing whatever product they want. Okay, this is called as nesting. So, nesting itself is a big algorithm. So, you have a sheet metal, you have a product, how many parts can be made, what all orientations I can do. It is not necessarily all has to be in one direction, you can do it anywhere, but you try to reduce the scrap. So, ensures maximum stock utilization. The diameter of the pierce hole should not be less than the stock thickness. Keep that in mind. The spacing between the holes should be minimum of twice the stock thickness. So, that is what is required, so that you can try to do stamping operation. This is also holds good for elastomers and plastics. So, today's task for the students are going to be a fun task. So, try to take the finger chips which is ready made available. Try to put it in a pan where it is with oil, right. Try to drop it inside a pan. Okay. So, here what you do is the temperature of your pan, oil pan, is fixed. Okay. So, now what you do is you try to vary the time. So, that means to say, so you have time maybe 5 minutes, 10 minutes, 20 minutes, 25 minutes, 30 minutes after the oil has come to a stable state. Okay. And then what you do is you try to take the performance. So, what you do is you try to take a finger chips which is already available, or take a potato. So, there is a potato finger chips. Take a finger chips, right, and it is ready made available today. Drop it inside the oil pan. This is oil. The temperature has come to a stable state, and then what you do is you try to, and here it is still burning, right, here heat is applied. So, it comes to a stable state to a large extent, and then here is a time. So, you just try to put the chips and then keep it for this. I have just put it as 5, 10 magnitude of my own choice. It can be 1 minute, 2 minute, 3 minute also, and then try to see whether you get a crispy shell, soft core. Okay. When do you get at which temperature, and then as and when you keep increasing the time, so it is going to stay there for a more time. So, you will see a crispy sheet outside, and the core also will become crispy. So, try to do this exercise. So, what I am trying to demonstrate here is, just by taking the constant finger chips workpiece material, dropping inside a heat treatment process, just by varying the time, you see different taste of the same material comes. So, it is crispy, so it breaks, or it tastes nice, and completely crispy is of a different taste, and the performance is different. So, this exercise, just try to do it for yourself, so that you will try to appreciate the heat treatment effect on the workpiece and its performance. Here we talk in terms of taste, but you can also make it brittle. So, it is brittle and other things. Thank you very much.